All right, so this is Mr. Jern, and I am going to talk to you today in my fancy little tie about Coulomb's law. Why a tie? Why not? It's Coulomb's law. It's exciting. And so on the screen right now, it says you're going to need a calculator today. Uh, and the only reason I would say that you should get a calculator is because in a few minutes, I'm going to go over a couple of problems, and it would be a really good idea for you to try to follow along to make sure you get the correct answers, because we're going to be working with scientific notation again. And you might not have access to a physical calculator, in which case you can maybe use something. I would recommend Desmos, because on Desmos, you can access that actually on the tests. And your cell phone, while it has obviously a calculator built into it, I don't know if I get used to using that, at least in here, this class. It's really a shame because, we carry a calculator around in our back pocket at all time, but they're not allowed on tests. And so Desmos probably, or if you have a physical calculator, that would be ideal. All right, so let's get into this Coulomb's law. First of all, in physics, we like to study things. I don't know if you noticed that. And the best way to study things, the most effective way to study things, the best way to get any meaningful observations and being able to predict anything out of what you're studying and be able to build models off of that, predict things, is to start assigning numbers to things and to start measuring things, quantifying them. And so, not surprisingly, scientists have quantified charge. Charge, the unit of charge, is a Coulomb. We represent charge with a lowercase q, and the Coulomb is the unit. So you might see something like the charge is, 5 coulombs. Okay, that's what this is being. So charge is lowercase q, and coulombs is the unit of measurement. The relationship between charge and force is linear. What that means is as force increases, so if we were to graph this and we were to put force on one axis and put charge on the other axis, you would see something like a linear relationship. As force increases, then so does charge. In other words, if you take two objects, two balloons, two whatevers, and you increase the amount of charge on a balloon, it's going to be able to exert more force. Okay, so in other words, if I rub a balloon with a rabbit fur and it has a certain amount of charge on it, and then I rub it more and I double the amount of charge, it's going to have double the force. Okay, so I could have probably, and it would have maybe made more sense to maybe make a graph like this, where if I double, where I have charge on one axis on the x-axis and force on the y-axis. If I double the charge, I will double the force. Okay, that's basically what it comes down to. What else? Yeah, okay, so that pretty much says what I just said. Okay, on the screen. As the charge of one object changes, the force between the object changes proportionally. As one goes up, the other one goes up proportionally. If one goes down, the other one goes down proportionally. Relationship between distance and force. Let me re-emphasize that. The relationship between distance and force is an inverse square. So if we were to graph the distance between, or just we'll say distance between two objects, the amount of electrical force, and maybe I should start adding a little e here, because we want to specify that's electrical force, would be an inverse square. So if you're really close, you're going to have a lot of force, and as you get farther away, it's going to decrease exponentially. That's what an inverse square looks like. What the heck does inverse square even mean? You might not have ever heard this term before. Well, it means exactly what it looks like. Inverse square. Inverse square. So you all know what a square is. It's like basically take a variable, take a number, and you square it. And inverse means you take 1 over that. You take the inverse of that. So that's what the square is. So let me give you some examples here. Actually, first, as the distance between the object changes, the force between the objects changes inversely to the square of the distance. Okay. So I got a graph, I got a little like 1 over x squared, but that doesn't make you feel or understand maybe what inverse square is. So let's take a look here. On the electric field hockey simulation you've done, amazing simulation for seeing this. if you have two charges, if you've got a charge, a positive and a positive charge right next to each other, and you could see this arrow here represents the force that the black puck here is feeling by the red puck. Okay, so it's all about the black puck. What is the amount of force? Obviously, Newton's third law, the red puck would feel the exact same force in the opposite direction, but we're just focusing on the black one right now. So this black positive charge has a certain force on it. Now, what would happen if you were to move this red positive charge closer, as in like you cut the distance in half? Would you feel twice the amount of force? No, you would feel 4 times the amount of force. Okay, like the black puck here, the black, I call it the puck because of the electric field hockey. So the black positive charge here would feel 4 times the amount of force. Okay, you could try it on that simulation. You cut the distance in half, the force increases by 4. Okay, that's the square part. What about the inverse part? Well, the inverse part is the fact that the distance decreased, not increased. Sometimes seeing the numbers actually also helps a lot. So if I take a little chart here and I've got distance on the top and I've got the amount of electrical force felt on the bottom, if I have a certain distance, we'll call it just 1d, 1 times the distance, and I have the object is feeling a certain amount of electrical force. Okay, we'll just leave it at that. Now, what happens if I double the distance? Well, it's going to feel 1/4 of the electrical force. Inverse square. What do I mean inverse square? Well, what happens when you square a 2? 2 squared becomes 4. What's the inverse of 4? 1/4, 1/4. So you got your inverse square. You're going to feel 1/4 the electrical force. What if you triple the distance between the two objects? Like picture 2 balloons just hanging from strings on the ceiling, right? They are feeling a certain force between them. They're pushing on each other. They're repelling each other. So what happens when I triple the distance between them? How much force are they going to feel? 1/9 the force. The electrical force is what they're going to feel. Inverse square. What if I have 4 times the distance? So now I'm holding those balloons really far apart. 4 times the original distance. Inverse square. They're going to feel 1/16 of the electrical force. See how this is going? 5 times the distance. That's right. They're going to feel 1/25 the amount of electrical force. All right, what if I cut it in half? Instead of getting farther away, I got closer. Well, 1/2, 1/2, you're going to feel 4 times the amount of electrical force. How'd that happen? Okay, inverse square. In this case, I like to inverse it first. So 1/2 becomes 2/1. 2. Square 2, you get 4. Just look at this again. What about 1/4 of the distance? 1/4 the distance. Well, inverse square of that, you inverse 1/4, you get 4/1, and you square it, it's going to feel 16 times the amount of electrical force. 1/5 the distance, getting closer and closer, it's going to feel 25 times the amount of electrical force. All right, you starting to see this pattern here? That pattern, let's finish this up, 1/6, we're getting really close, 1/6 of the original distance. The force between them will be 36 times the electrical force. That pattern is an inverse square pattern, okay? So when I say inverse square, that's what I'm talking about, okay? If you can remember this pattern, you have remembered, you know what an inverse square law is. And we're going to see inverse square laws with other things, but for now we're looking at Coulomb's law. And it has to do with the fact that it's going out in a circle, not a circle, a sphere. So anything that kind of like spreads out in a sphere, sound does this, light does this, all sorts of things follows the inverse square pattern. Alrighty, so let's take a look at this. What happens to the electrical force? So let's apply this. What happens to the electrical force in the following cases? What happens if you double one charge and you double the distance? Well, if you double one charge, you're going to feel 2 times the force. And if you double the distance follows the inverse square law. So if you double it, meaning 2 times, you're going to feel 1/4 the electrical force. So the total together, you multiply those together, and you get 1/2 the electrical force is what you're going to feel. All right? What if you double both charges and double the distance? Doubling both charges, okay. The amount of charge, excuse me, the amount of charge, remember charge is directly relation. It's proportionally related to the amount of force felt. So if I double both charges, then both charges are going to be doubled. And I double distance between the two charges. Doubling the distance follows the inverse square law. And so we're going to get 1/4 the distance. Multiply those all together. The total effect is going to be 2 times 2 times 1/4. And you're going to feel the same amount of electrical force as originally. Have. Okay, seeing the word have written out is kind of a weird, like we might not be used to that. That just means half. It's a verb. Like you're halving it. You're cutting it in half. So one charge has been cut in half. It's been halved. And the distance has also been halved. How much electrical force would you feel? Well, because charge is it's got a direct relationship, proportional, you're going to feel 1/2 the electrical force. And halving the distance, that's going to, so half the distance, that's a 1/2. And then if you inverse that and square it, you get 4 times the electrical force. And so you multiply those together and you're going to feel a total of 2 times electrical force. Triple one charge and quarter the distance. All right, things are getting a little ridiculous, but it's an exercise. So we're just trying something out. Tripling one charge, you're going to feel 3 times the force because you're tripling the charge, and 1/4 of the distance. So 1/4, if you inverse square that, you're going to get 16. Multiply 3 times 16, you're going to feel 48 times the amount of force. Okay, see where this is going? All right, I know you can handle this. Have one charge and double the other. Okay, now, this question is good because a lot of students would do this wrong because you see a pattern and it's like, okay, I gotta like multiply by whatever, and then I do the inverse square. Be careful. Distance follows the inverse square. Distance. Charge does not. Charge is just a direct relationship. What's not even mentioned here? That's right, distance. So watch out. Be careful what you're, like make sure you're answering the question that's being asked, not the question that you think is being asked. So having one charge, direct relationship. Doubling the other charge, direct relationship. Multiplying by each other. There you go. No overall change. Okay, so those are just some exercises that you can try to make sure you understand working with the relationships between those. So finally, a couple questions to answer, some examples to follow. What is the force between and see, here's where we get our scientific notation. You got to understand, charge involves very small numbers, all right? When you're talking about charging a balloon, for example, you got to realize, I mean, there are countless electrons that get transferred from the fur to the balloon, like unbelievable amount. And each one of those little electrons carries a tiny itty bitty charge, as you see here, but they add up because there's just so many of them. So unfortunately, charge is just a small number per electron, and so we're going to end up using scientific notation because we don't want to write a bunch of zeros and get messed up with that. Now that there's something I'm about to show you in a moment that's going to also involve scientific notation. So what is the force between a 2.1 times 10 to the negative 4th Coulomb charge and a negative 3.2 10 to the negative 5th charge? If they are this distance apart, 3.4 times 10 to the 1 meters apart, so it's not very far apart at all. Okay, do they attract or repel? So we got kind of a two-part question here. Now, you can actually answer that second question right away because you see we have a positive charge here, we've got a negative charge here. Positive and negative, what are they going to do? They're going to attract. So we will see that played out in the math. But what the heck do we even do with this? Well, let me introduce you to Coulomb's law. Okay, everything I said about Coulomb's law is great explanation, whatever. But remember, to really understand something and be able to predict and make models about something, we got to get the math involved. So if you look at your equation sheet, you'll see Coulomb's law. This is Coulomb's law. What it means is the electrical force is equal to some number K, which I'll talk about in a second, times Q1 times Q2. Q1 and Q2 being the two charges, divided by the distance squared, the distance between them squared. Okay, now if you Google this, you might see it's slightly different variables being used for this, but that's okay. It's the same relationship. The variables don't matter. The names of the variables don't matter. For our purposes, we're going to keep distance as the distance between the charges and the two Q's being the two charges. It doesn't matter which Q is Q1, which Q is Q2. You know, the charges are the same, doesn't matter, or doesn't matter which one we use. But about that K is a constant. It's called the charge constant. And that is also on your equation sheet. And as you can see, it involves scientific notation because, as you can see, that is a very large number. So K is a charge constant. It just kind of, for our purposes, it's just the relationship between force and distance and charge, as you can see by the units involved. K is 9.9 times 10 to the 9th Newton meters squared divided by Coulomb squared. All right. So, which is nice because we're dealing with newtons, which is the force, meters, which is the distance, and C, coulombs, which is the charge. So what do we do here? Well, let's start by just listing everything. I'm just going to say Q1, the first charge, is our positive 2.1 times 10 to the negative 4th coulombs. We'll call Q2, again, it doesn't matter which is which, is going to be our negative 3.2 times 10 to the negative 5th coulombs. The distance between them is 3.4 times 10 to the 1th, I like saying that, meters. And we want to know what is the electrical force. So we've listed our variables. We've got our equation. I'm not going to, we don't have to rearrange it at this time or anything like that, although you should be able to rearrange it and solve for anything. Sometimes they'll give you the force and you have to solve for one of the charges. Sometimes they'll give you the force and the charges and you have to find the distance. So be prepared to rearrange that equation to solve for whatever you need. So my electrical force is equal to K, 9 times 10 to the 9th Newton meters squared per Coulomb squared, multiplied by Q1, 2.1 times 10 to the negative 4th coulombs, times Q2, where are we at? Negative 3.2 times 10 to the negative 5th coulombs. All that divided by the distance squared. 3.4 times 10 to the 1th meters. And guess what a lot of students forget to do? That's right. Forget to square it. Please do not forget the square. All right. So how do we handle that? Well, let's put that into our little calculator, shall we? My calculator, there it is. Can I move that around? You know what, doesn't really matter. I don't have to. All right. So I got my old TI-83. It's kind of similar to, well, it's not similar. It's old, but that's okay. It's still going to do what we needed to do. All right. So I need to put this all in my calculator. And I'm going to use that E button I told you about. So on my calculator, there's E down there. I don't know if you can see it. It's pretty small, but where's my, let's do this. Woof. Okay. It's also a lot of focus right now. There we go. So this green E, where we go? This green E is not it. That's as part of the alphabet, A, B, C, D, E. So look out for that, especially if you have a graphing calculator. We're looking at that EE right there, that in yellow on my calculator. Okay, yours might be slightly different, probably is. And so I'm going to put these numbers into that calculator and I'm going to see what I get. So I'm going to use parentheses, scooch this down a hair, or better yet, let's just move the, scooch it down a little bit. So watch how nice this looks when I use the E. 9, where's my E? E, 9, that's a Q, 9. You're going to use 9E9 a lot in the coming days, times 2.1 E, so times 10 to the negative 4th. Make sure you use the negative sign. and not the subtraction, times negative 3.2 e negative fifth, and divided by parentheses. When in doubt, use parentheses. I could use more parentheses if I want, but I'm not gonna. 3.4 e 1. That's okay. And then the part that you might forget, square it. All right, and I get my answer. It's not in scientific notation. That's probably okay. Let me just scooch that over a hair here. So what are they gonna feel? Where's my little, it's nice if I hold my pen right side up. So when I do that, I get negative 0. We'll call it 5.2. Okay, now this is the fun part. I like doing this. We got coulombs. That's gonna cancel out the coulombs on the bottom there, and the other coulomb will take care of that square. We've got meters, which are squared, will cancel out with that meters squared right there. That leaves us with just newtons. So we're gonna feel a force, electrical force of negative 0.52 newtons, which in our case means that they're pulling toward each other, which is great because that means they're attracting. All right, got one negative, one positive. So the amount of force, I'm just gonna re-add that right here, the electrical force is equal to negative 0.52 newtons. And that's how you do it. Okay, so take a look at my little calculator. I didn't bring home one of the TI 34s that I have at school, but it's basically the same idea. I kind of like this because you could see the entire screen, and you can see how I did that. So now, at some point, practice this on your own using Desmos, or if you happen to have a calculator that's able to do E, then do that. If need be, you can use your phone just to kind of like try a calculator, but honestly, use the calculator you'll be able to use in school. All right, let me just kill that for now. How many electrons does it take for an object to gain negative 0.5 coulombs of charge? Well, that seems like a strange question, but it's not, because we have another equation to work with. Q equals NE. So this is not really part of Coulomb's law, but it's definitely related. The amount of, what this is saying is the amount of charge, Q, so this will be Q right here, is equal to N times E. Now N, you may have seen this in a math class, is just an integer. It's just a number. In other words, how many? This will be N. E is the charge of a single electron, which you're not expected to know that. That's given to you. It's right around where around where K is at on the equation sheet. E is the charge of a single electron, and as you can see, it is very, very, very small. 1.6 times 10 to the negative 19th coulombs. Okay, very small, but electrons are also very small, and there's a lot of them, so they gang up and they add up a lot. So we want to know how many, so N is going to be our unknown. We got a charge that it gains of negative 0.5 coulombs, and we know E, so E is going to be our constant, the charge of a single electron. So in this case, we do have to rearrange our equation a little bit. We want to solve for how many, so this isn't going to be too shabby. So N is equal to Q, the charge, divided by the charge of a single electron. So then I'm going to plug in my numbers as best I can here. Now here's the thing to remember. What's the charge of an electron? I mean, obviously there's the number, but what's the charge? Is it positive or is it negative? All right, so Q, it says we want to gain negative 0.5 coulombs of total charge. But what's the charge of a single electron? It says 1.6 times 10 to the negative 19th. That's okay, but negative because it's an electron. So negative 1.6 times 10 to the negative 19th coulomb. So I'm going to put a big old arrow there. So if you kind of like are dozing off during my video, why is that negative? Because electrons are negative, okay? Negatively charged. So there we go. Now, why I say so, but I haven't quite solved this yet. So let's put that into our little calculator. Man, I love pulling up my little, okay. Let's do that. Let's move that back over here a little bit. And so for this one, negative 0.5, you could put the 0 in there. You don't need to, it's the calculator. Divided by negative, excuse me. You know what? I got that. I'm going to use my parentheses here because of the scientific notation and the exponents. Negative 1.6. No, wrong button. Times 10 e negative 19. So that's another number you're going to be using occasionally. Not as much as 9e9, but that's the charge of a single electron. And so our answer ends up being 3.1 times 10 to the 18th. What's our unit on that? Let me get rid of the calculator for a second. It's a little distracting. Oh, there it is again. All right. So what's the unit on that? Well, great question. Look at this. Coulombs cancels out. We have no unit. That's okay. It's an integer. An integer is just a counting number. It's like, how many do we need? Well, that's a lot of electrons. 3.1 times 10 to the 18th. Yeah, well, remember, they're very small and they have a very tiny charge. And we want a charge of negative 0.5 Coulomb. So we're going to need a lot. Okay. So that is your basic introduction to Coulomb's law and an example question. Just remember, just keep like you've always done in physics, just identify the variables, identify the equation that you're going to use. Be careful with negatives, be careful with squaring. Like I said, the square right here, a lot of students forget that. The negative, the worst that's going to happen is you'll get a negative number here, which doesn't make sense. So just that'll be a little reminder to use a negative. All right. So please let me know if you got any questions and take care.